properties of determinant prove that the determinant, let me call the number arrangement inside by matrix. Let A be a matrix, C 0, negative A, B, A 0, C, minus B, minus C 0. Consider this matrix. And what have we to prove now? We have to prove that determinant A, where A is a matrix, equal to 0. That's what you have to prove. Now just observe this matrix very carefully and tell me what is transpose of it. By the way, how do you get the transpose of a matrix? Interchange the row and column. So write the elements of first row, 0, A minus B in the first column, minus A, 0, minus C in the second column, and B, C, A in the BC 0 in the third column. And do you find that we can take a minus sign common? So make a change of sign for all the elements. Of course 0 will remain 0 and you get A minus B, and here you get minus A, 0 minus C, and you get BC 0. And now look at 1, the given matrix A. What do you find at this stage? Isn't it minus out, and the matrix, what about this matrix? 0, A minus B, etc. Isn't it same as the given matrix A? Yes, from 1. So what have we proved by now? That A dash, the transpose of matrix, is same as negative A. So what type of matrix is this that way? It is a skew symmetric matrix. That just like that, we have nothing to do to mention it is skew symmetric, but later after proving this question, I will state a result. So A is a skew symmetric matrix. Then I would try to generalize that if given matrix A is a skew symmetric, what will happen to determinant A? That I will generalize later. And now we have to prove that the value of determinant A is 0. Okay. So consider determinant A. You know by property that determinant of A dash is same as determinant of A. That is, if you interchange the rows and column, then value of determinant remains the same. So determinant, the required determinant A should be same as determinant of its transpose, obtained by interchanging the rows and column. You know that is the property 1. But here we proved in second, say this second, that transpose A is negative times A, or negative 1 times A. That's the same thing. Negative 1 times matrix A. Do you know a result? Now, in previous question we proved this result. Please make note that the determinant of K times a matrix A is K cube times matrix A. Of course, A is a matrix of third order. So if A is a matrix of third order, then determinant of Ka will be K cube times determinant A. So using this, you had determinant A equal to minus times matrix A minus 1 time, and this is a matrix of third order. So the determinant value will be K cube, means minus 1 cube times determinant A, that is minus times determinant A. After all, determinant A is a real number. So if the value of determinant A is negative times determinant A, or in other words 2 times determinant A is 0, so clearly the value of determinant A is 0. Now before I leave this question, please make a note, though the question is over. This determinant A we have proved 0 for matrix A. What kind of matrix we found that A was? It was a skew symmetric. So please make a note in general that if A is a skew symmetric matrix, then the value of determinant A will be 0. It could be asked as a 1 mark question somewhere that you are given a determinant whose matrix is skew symmetric. So just by observation immediately we can say that it is 0 instead of expanding in detail and so on. Question 7. Using the properties, prove that the determinant value is 4a square b square c square. What is the given determinant? The elements of the first row are minus a square, ab, ac. Second row are ba minus b square, bc. That of the third row are ca, cb and minus c square. Very clearly we find that each element of row 1 is a multiple of a, or a can be taken common from row 1, similarly b from row 2 and c from row 3. Just to simplify it, and we have not to evaluate it right in the beginning, we have not to expand it, as I told you, maybe after 2-3 steps we can. So taking a common from row 1 and similarly taking b common from row 2 and taking c common from row 3. The given determinant reduces to the given determinant, just denoted by delta, the given determinant delta a, b, c common. Take a common from row 1, you get minus a, b, c left. Similarly, when you take b common, you will left with a minus b and c, and take c common from third row, you get a, b and minus. Observe very carefully to the determinant. Don't you find that now a is common in column 1, b in column 2 and c is column 3. So now you take a common from column 1 and take b common from column 2 and take c common from column 3. So now your determinant is a, b, c was already there, and again you are taking a, b, c common. And what are the elements now? The elements will be negative 1, 1, 1, and you get 1, negative 1, 1, and 1, 1, negative 1. So you get the value of determinant is now a square, b square, c square we get outside. And now what do you see? It is very simple that if you add R1 and R2, you will get 2 zeros, and similarly you add R3 and R1. So what we do, keeping R1 the same, keeping the first row same, you apply R2, we change to R2 plus R1, and also to R3 we add the elements of R1, keeping R1 the same. So R1 continues to be minus 1, 1, 1, and now to the elements of R2 you add R1, so you get 0, 0, 2, and similarly you add R3 and R1, you get 0, 2, 0. Now it is very convenient to expand it, and obviously there being 2 zeros in column 1, so expand with column 1. Of course, a square, b square, c square are outside. When you expand, it is negative 1 times the elements of the main diagonal, delete the row and column through minus 1 are 0 and minus 2 into 2, 4. And of course, no doubt, other two elements will be 0, 0, other two terms, So now you get a square, b square, c square into minus 1 into minus 4, minus 1, minus 4, 4. And that is the required result. The value of determinant comes out to be 4a square, b square, c square.